All right, everyone. So how was your weekend? Good, good, good. So how's everybody doing on the how'd everybody do on the assignment that was due Friday? The recursion and the Sudoku? Uh-huh. If you still feel like you want to do the extra credit, you're more than welcome to do the extra credit, as it's going. So for the next homework, it's actually going to be, this homework's one of those nice breaks, I feel. It's considerably easier, but still a bit of work, but considerably easier because a lot of this stuff can be gotten from the textbook and from the from my own, typing. So this chapter is on trees, right? So now these trees are not the trees that. So I'm going to go ahead and talk about it, and then I'll let you guys get to what you need to do. There will be a quiz on trees on both Wednesday and on next Monday. On the tree quiz that's coming up will be a definition-based quiz. And then on Monday, we're going to do a quiz on adding and removing items from a tree. So those will be very similar to so both the first question and both the first quiz and the second quiz are going to be very similar to what you will get on the second exam, which will be in I say probably 3 or 4 weeks, depending, right? It's because we're going to do, let's see. So this week, not next week, because that's going to be heat. The week after that is going to be hash maps. So probably the week after that will be the quiz. That will be the next exam. Now the next exam is mostly going to be theory-based as opposed to a lot of the programming you had to do. Because there's a lot of figuring out how things work. So this quiz will be the quizzes will be very similar to the exam questions you're going to get. Which is, given these numbers, how do they go into a tree, what order they appear in, and what are the definitions for the trees. All right, so we've been dealing with data structures that are lists. They deal with ordered data, or they can deal with unordered data, but trees specifically deal with a certain type of data. They deal with data that has an order, or in Java, as we call it, comparable. So when we do a declaration for a tree, let me go ahead and see this. I don't think I put the hotkey back in for this. Why am I bothering to write? Why should I bother writing something? Should put it over here so you guys can actually see it, right? And actually, actually be able to read it. So when we see a tree, trees work off of data that has an order because it's going to sort stuff as you put things into it. That's kind of a nice thing about trees. So binary tree, as you'll see in the videos that I build it up, they were some of the first lectures that I did. So you'll see I'll be working on a Windows computer and be using some mad MS Paint skills. They'll look like this: public class binary tree that holds not E, but they'll hold E extends comparable E, which seems like a mouthful. But all this is saying is that we're putting this extends put some restrictions on what can get stored in the binary search tree. It says this stores E's, but what kind of E? But what is an E here? Well, if I didn't have this, an E could be anything. But with this, I'm saying the E has to be comparable. So we can only put in things that have the compare to method in there. So we talked about the compare to method. Okay, the compare to method, right? So that's built into integer. It's built into a bunch of other classes. Anything that can be ordered, it's built into. So let's go ahead and test it out on strings and on integers. So let's go with JShell. I love this thing because it allows me to just throw things on the board. very quickly. Okay, so integer I is equal to 7. Let's go with actually A. A is 7, and B is 5. Okay, so A dot and I can use a method because it's an integer, right? It's an integer class, not a primitive, right? A dot compare to B, and that will return, and that returned to 1. Okay, A dot compare to B, return to 1. Interesting. What about B dot compare to A? That returned to -1. So the way that compare to is defined, it's an interface. So anything that implements the comparable interface is comparable. It can be put in an order. And you check the order of things using the compare to method. It's essentially a test to see is it greater than, less than, or equal to. And if A comes after B, it returns 1. However, let's go ahead and change this. Let's go ahead and change B to 12. If A comes before B, it will return -1. Actually, technically, what it will say according to the specifications, if A comes after B, or A is greater than B, then it will return a positive number. If A comes before B, or is less than B, right, in that case, then it'll return a negative number. Okay? Any guesses as to what it will do if they're the same? It'll return 0, right? That's kind of, what is it, the Squeeze Theorem or something? I'm trying to remember what it is in calculus. You can squeeze. Yeah, so you can figure out, so right. It's less than, greater than, So great. Well, and we can just test it out. A compared to A returns 0, right? So, but it doesn't necessarily have to be like that. For instance, hello dot compare to world, right? Strings are comparable. It gave me -15. Now we know that hello is before world. This means that, it means hello is before world, but how is a string before another string? What kind of order is that? Alphabetical, right. So compare to compares strings and says they come alphabetically, right? So it depends on the class how things are comparable, okay? So strings are comparable alphabetically, and this -15 kind of tells me like how much before it comes, right? For instance, if I were to say A dot compare to C, let's see, say -2. A is 2 before C. What about AB compared to C? -2 still, right? So it compares things in alphabetical order. Now, most of the time we don't care about it. All we care about is it less than 0? Is the result less than 0, greater than 0, or equal to 0? So you're never going to have to, so in this class, you're never going to have to implement comparables, right? You're just going to have to use compare to compare comparable things, right? So anything that has the compare to method, the binary search tree will do. This means that we can assume, so by putting this in, we can basically write a method that would assume that things have the compare to method. Because of this, this allows us to assume that the compare to method will actually be there. So I could write something like public void. Yeah, let's go ahead and do public void. Public Boolean in order, right? And it will check if A becomes before EB, right? Does A come before B? And all we have to do in that case is that we can return A dot compare to B. A dot compare to B is less than 0, right? So we can write something like that, and the main thing to show you is that compare to won't give you an error. if you've extended comparable. Okay? You might have to import comparable, and possibly spell it correctly. I'm not sure if I did that. So, but if you compare this to the, but here, as long as things are comparable, you can assume that you can use the compare to method, which is pretty nice. Okay, so let's go back to the discussion of trees. Okay, so trees automatically sort stuff as it comes in, and it's a fairly straightforward algorithm to build a tree, which I'll just go over now. And I assume you're going to watch the videos or have watched the videos, but I'm going to assume that you haven't yet because, I sent that out on Sunday. The next chapter will be related to trees. They'll have the same structure, but they're not going to be binary search trees, right? The next week, will be something called heaps. So a tree looks like this. And I know this doesn't really look very much tree-like unless you're looking at like a family tree kind of thing, right? And I suppose this, and furthermore, we call this part the root, the thing at the top the root, and we call these the leaves at the bottom. And I just presume this is because programmers don't go outside very much. So hence the confusion. But I digress. So a tree, this is specifically what we call a binary tree, meaning that everything has anywhere between 0 to 2 children, right? So we have each node. Each node has basically multiple branches going down from it, right? So this guy over here, he has 2 children. He has one child, a left child, and another child, a right child. Named because one's to the left, one's to the right, okay? And it looks something like this, typically with data. What it will look like is we've got maybe a 15 over here, and I'm just making up numbers according to some rules. So 15, let's go with 20, 17. Let me make these bigger. 15, 20, 17, 25. And then over here on this branch, I'll go ahead and do 5, 3, 7, 6, 9, 8. Okay? And there's an order to this madness. Okay? Now, a binary search tree, this tree stores all the numbers that you see before us. 3, 5, 6, 7, 8, 9, 15, 17, 20, 25. And what's magnificent about trees is that on average, a call to find anything in the tree, to retrieve anything in the tree, takes log n time, as you'll find out. So adding something in the tree will take log n time. Removing something from the tree will take log n time. Seeing if it exists in the tree takes log n time, on average. It's actually quite nice. So it's kind of the jack of all trades for data structures. It's pretty much got a fairly good runtime for everything. Okay, so let's talk about this guy. So how is stuff kept in order? Well, it's pretty simple. The first rule is that anything that is less than the root goes to the left of the tree. Goes to the left side. Everything that's greater than the root goes to the right side. That's the first rule. There's only 2 rules. First rule is everything to the left, less than goes to the left. Everything greater than goes to the right. Okay. What about equals? Make it up. Let's go ahead and just assume. I always treat equals as I always treat equals as less than, just to make it easy. But you can also treat equals to as, a special case. Okay. Second rule is that it's recursive. And so that's why we learn recursion before we do trees. This is a recursive property. So each node in the tree, you can look at it as though it's the root of its own tree, of its own subtree, as we call it. So 5 is its own tree, and everything less than 5 goes to the left of 5. Everything greater than 5 goes to the right of 5. Right? See that? 3 is less than 5. 7, 6, 9, and 8 are all greater than 5. Furthermore, 7, all the stuff less than 7 goes to the left of it. All the stuff greater than 7 goes to the right of it. And 9 over here has all the stuff less than it in the tree go over this way, and everything greater than 9 goes over here. at least down by its level, right? So 15, right? 15 has all the stuff less than it, all the stuff bigger than it. Now, the order that stuff gets into the tree, at least for the binary search trees that we program in this class, it just simply depends on the order in which stuff happens to be added and removed from the tree. So that's why 15 is the root, because I happen to write 15 to be the root. Yes?
Could you, in theory, have 16 to the right of 9?
In theory, no. But that's an excellent question. I cannot, in theory, put 16 to the right of 9 because this is a recursive property. So all the stuff that is less than, only stuff that is less than 15 can go to the left.
So would we have like a place method and it takes like the root element in an array?
So so we're going to use nodes to do this.
Okay.
We don't use it. We aren't going to use an array for this. And it's very and what we do have is an add method. So let's see how that would work. Okay, an add method. Say we wanted to add 16 to this tree, right? So we'd say add 16 to the tree, and we would start at the root. Much like a linked list keeps track of the head, we will keep track of the root. Okay? And what we do is we compare 16 to 15, and we ask ourselves, okay, how does 16 compare to 15? Is it less than, equal to, or greater than? Okay? Or is the spot I'm adding it to empty, which is our base case? Okay? So it's not empty, so it's not less than, not equal to, so 16 is greater than. So that means we have to add it, that means that 16 goes to the right side. So we are going to add it to the root of the right subtree, which is this guy over here. So I then repeat the same add algorithm, but from here. Okay? So now I compare 16 to 20. 16 is less than 20, so it's going to go to the left. Okay? What about 16 and 17? 16 is less than 17, so it's going to go to the left. And then we have 16 an empty spot, so we now have found a place to put 16. Okay. So we put 16 over there. Okay? So where we put things and it's on top of 9 simply because I'm a terrible drawer and I'm out of room. So now, why is this? So I mentioned that this is log n time on average, and why is this? The reason is because if you add something to the binary search tree, right, we're going to either be finished or we're going to go to the left and the right. And on average, half the things are going to end up in the left, half the things are going to end up in the right. So if I decide to go to the left, that means I don't have to examine anything on the right. If I go to the right, that means I don't have to examine any items to the left, which is half the items. And then that just simply, that halving process continues. Then I throw out a quarter of my search space, then an eighth of my search space. So it ends up, so this dividing in half each time, it's like a binary search. So that's why it takes log n time to add anything, because we're continuously adding stuff. So it's pretty nice. Removing is a bit trickier, and we'll get into that in the videos. There's multiple cases, but to remove something from a tree that's just a leaf, and a leaf is a node without any children. So for instance, if I just wanted to remove 16, it's pretty straightforward. I just literally remove it because it doesn't affect the order of the tree. It's when you are trying to delete something like 7 that it really becomes a pain in the butt. Now, so we're going to be just going over basic binary search trees in this chapter and this week. However, you should know that there are chapter 9 goes over what we call self-balancing binary search trees. Because I've thrown this caveat word up, on average it takes a log n time to add something to a tree. Worst case scenario, though, if we're adding something to a tree, since the order that I add stuff to a tree matters, if I added 1 to the tree, it's an empty tree, it would just go like this. Okay? This is 1. Added to the tree. Now let's say I add 2 to the tree. Okay? 2 is greater than 1, so it goes over here. Okay? Let's say I add 3 to the tree. 3 is greater than 1, 3 is greater than 2, so it goes over here. What if I add 4 to the tree? Right? 4 is greater than 1, greater than 2, greater than 3. Can you guess what I'm going to add next? 5. Yeah. So 5 is greater than 1, 2, 3, 4. And so if I keep doing this and I'm just continually adding things, then I'm essentially just turning the tree into a glorified linked list, right? Which means that it will take O of n time to do anything. Now, That being said, this doesn't really happen too often, right? First off, it typically looks, the tree shape when you get an unbalanced tree, a phrase which I am deliberately not defining, but you can kind of grok the meaning of. Unbalanced tree looks something like this, where basically going one step only gets rid of like one or two choices. Right, where just zigzags. Right, that's typically the way an unbalanced tree looks. We don't want that to happen, so in real life what we use is something called a balanced binary, or self-balancing binary search tree, which at some points detects an imbalance and then fixes the imbalance in log n time. So that's not something we're going to get into, but it's in chapter 9. But things like red-black trees, B trees, B plus trees, 2-3 trees, they all like self-balance and stuff and fix themselves to make sure that in real life that it's always log n time and we never have to deal with a O of n case. All right. So questions before you start looking at the homework and stuff. So the homework for this week is we are going to build something called an index tree. Okay? And what we're going to do is that we are going to basically build essentially the index for a file, much in the same way you could build an index for a textbook or something, right? So for every given word, I'd like to know what lines that word appears on, okay? So most of the time, right, it's not really too useful to just store numbers or something in the tree, right? Really what we use trees for sometimes are the same things we're going to see we use hash maps for, or dictionaries for, which is key value pairs. So here, what we want to do is we want to store the words in our tree. That's what we call the key, the thing that basically that we are categorizing, and then or we're looking at, and then we're going to so each node is going to store the word, and I've given you the node class, by the way. You don't really need to add anything to it other than completing the methods I ask you to complete. Okay. And then the next thing you want to do is basically, so each node keeps track of the word and then a list of all the lines that word appears upon. Okay? And the way you're going to do that is you're going to read a file, which in case you didn't do it last time, I provided you a example file for. Okay?